Okay, good morning to everybody. I started recording the lecture. I see that we are 15 people connected since a few minutes, so I think we can start. Maybe somebody else will join later on. Okay, please start Lusa's modeler and also download or open the PDF that we discussed last time with the content of today's exercise, today's practice lecture. I'm going to launch the Lusa's code, and okay, I will share the screen soon. Okay. Can you see the screen with Lusa's modeler? Okay, thank you. Okay, we are 19 now, so I would like to ask our collaborator, engineer Rinto Roy, to turn his camera on and also his microphone and introduce himself. He will help us during these classrooms. Maybe sometimes he could join Group B instead of Group A in the future, but okay. Good morning, Rinto.
Thank you, Gianfranco. Hello to all the students. It's it's nice to meet you guys, and it'll be fun to work with you for over the next 2 months. So obviously, I'll be helping out Gianfranco and Francesco for this course. So in case you have any doubts with regard to using the software or anything regarding that, you can always ask in the chat. I'll try to reply. Obviously, the other two tutors will also be working on it. But yeah, usually we hold this lab session physically, where we can actually see your screen and actually see what you're doing. But unfortunately, we can't do that this time. So it'll be more difficult to answer questions and doubts. So, but we'll try our best, and hopefully everything will work out. So, thanks again, Gianfranco, and I'll let you speak again.
Thanks to you, Rinto. Okay, we will create, or we'll do right now, a separate room for the moment. Okay, I will allow you to join that separate room and 100 minutes create. Okay. Here, on the left of your screen here, you should see stanze separate or separate rooms, or I don't know, breakout rooms, something like that here. So in that case, in case if Rinto is inside the room, if you have special questions, you can enter that room and one by one, maybe, and show your screen and discuss with Rinto, maybe later on. But in case you enter that room, a new window will be opened, and you have the possibility to come back to the main virtual classroom, the main room, or move to the separate room. I ask you to leave it once the question has been answered, okay? Okay, here I stay here and okay. Okay, we can start. At least at the beginning, I wish to recall what is the content of today's lab. So basically, this is the structure. We want to model it in LUSAS, this finite element code, and compare the numerical results with the analytic solution. Of course, we are able to calculate very easily the analytic solution for this simple problem, and we will get the results by the finite element code and make comparisons. Okay, this is a cantilever beam with a concentrated force at the free node B. F equals 400 newtons downwards. The beam is 1 meter long, clamped at point A. So at A we have a fixed support. Okay. It is made of steel with these material properties: Young's modulus E and Poisson's ratio E here. And then beam cross section is rectangular. The beam has rectangular cross section of width B and depth H. It is 30 by 40 millimeters. Okay. Here we have the main properties: cross-sectional area and bending moment of inertia, second moment of inertia. And these are the two basic quantities that we at least need to enter to assign to the model in case we model the beam as an Euler-Bernoulli beam. So only considering the bending deformability. As a second step, we will also include shearing deformability by including the shear shape modified area and getting different results. Here we have, in terms of attended results, on the left, this is the convention for the internal forces, coherent with the LUSAS axis that we will use. So X will be the centroidal beam axis, and small y, small x, and small y will be the transverse axis. So that we have the axial load N directed as X, axial force N, then the transverse or shear force Ty, and the bending moment Mz, because Z is the axis perpendicular to the figure, okay, to the sketch here. So basically, internal forces N, T, and M are functions of the longitudinal coordinate X, and in particular, in this beam, the axial load is always zero everywhere. The shearing force Ty is constant and equal to minus F, and the bending moment Mz is linear with X, and it is 0 at B, at the free end, and the maximum equal to F times L. So the applied force here times the distance L at A. And so this is the linear shape of the bending moment diagram. Reactions at the support will be the vertical reaction at A, which coincides with the shear at A, and the bending moment reaction, which coincides with the value of the bending moment at point A, so F times L, okay? So we will check the values of the reactions, external reactions, and of the internal force diagrams, M and T, okay? Here we will get, of course, a deflection curve, a deflected shape of the beam, and the maximum displacement will be, of course, at point B, here at point B. So the value of the vertical deflection at B is here from analytical formula at point B due to bending moment, so only considering the bending deformability is equal to minus, because of downwards, it is downwards, so minus 3.9872 millimeters, okay? This is given by the formula minus FL cube over 3E times I. E is the Young's modulus and I is the moment of inertia about the centroidal horizontal axis.